Today I'm going to just give you a brief overview of the Shield metric design application. Shield is a multi-component system. We have the NVH controller, which actually collects data and creates data files. We have the Shield PC application, which is what you're seeing, which is where we use those data files to design NVH metrics for pass-fail. And then we have Trove, which is our database management tool that brings all of the data into a database, allows you to create a permanent archive. So today we're going to focus just on Shield and give you a very general overview of how it works with a data file to design metrics and then ultimately create a configuration file which we can then deploy to an NVH controller and use in automated data acquisition and metric computations. So let's begin with a general tour of the front panel. You can see a time frequency diagram in front of you that represents the time versus frequency behavior of a dynamic data channel. In this case, we've got a microphone that was measuring a diesel engine that was going through a run-up when it was spun by an electric motor. And this is what's called a cold test. And we're after dynamic behaviors of the gears and the valves and the like that can tell us something about what's good or bad about this particular engine. There's also a turbocharger on this engine, and you can see this bright line here following my cursor that represents the blade pass frequency of the turbo. So in Shield, when we have a data file open, we can go to the File Channel tab here, and we can see the channel list. We have a couple of tachometers. We have an engine tach, which is a 4 pulse per rev optical tach that senses the rotation of the engine crank. We have a turbocharger tachometer sensing the rotation of the turbocharger spool. We have a couple of microphones, a couple of accelerometers in this data set, and we're going to look at what we can do with them to design metrics for pass-fail. So Shield is divided up into 4 primary tabs. You have your DAC and Utilities tab, where you do things like define your channel layout and set up triggers, which are the algorithms that find spots in the data file that are important to us. Preferences tab, defining file paths and the like. Channel test, which is a kind of scope tool that you can look at channels live and make sure sensors are healthy and working. And calibration, which is a utility that will put the NVH controller into a calibration mode, allow us to see the signals live and assign calibration values, assuming we put some kind of reference device on the channel. The signal processing tab, this is where we select the channel we want to analyze, perhaps define the time frequency behavior of the time frequency diagram, and then from there move on to order analysis, spectrum analysis, transient detection, and time angle series as the next step. And we always move from left to right as we walk our way through the Shield application and what it does. And we'll get back to this in a minute. The feature tab is here. The feature tab is where we look at the waveforms that we've defined in the signal processing tab and then turn them into single number metrics. So the curve you see would represent, say, an order cut versus RPM, and down here on the bottom we've turned that into a single number metric using a simple, in this case, extreme computation or a maximum. Once we define a list of metrics, we pop over on the decision tab, and here's where we define pass-fail behavior. For example, we have 3 decisions. Max 70-second order is greater than 80. Current value is in 88.2, and of course the part fails because that's larger than our limit. So what I'm going to do is work backwards through this list of metrics and show you how we actually came up with a 70-second order. So if I double click on this entry in this table, all the selections that were in place when it was created then become current down the bottom. So you see line 1, metric 1, fail, so we're failing. If that metric out of our choice of metrics that are defined, and there's a bunch of them in here, so that's the metric we're currently looking at, currently evaluates to an 88.2. If it's greater than 80 with no additional tests, so we're not comparing it to anything else, then we will basically cause the metric to fail. The metric is associated with a waveform. That's the waveform that this metric was designed with, and that's the max of 70-second order. The whole thing is then added to the table using the, in this case we can just hit replace. So now we have a test, a single test, and of course these other 2 were done the same way using other formulations. But let's work backwards now and take a look at 70-second order. So here's that metric on the list. There's the 70-second order waveform that represents the, in this case, one of the gear mesh harmonics of this diesel engine, which is a gear-driven valve train. So 70-second order is being computed by selecting the feature from the feature extraction list. Here, for example, is one of the other features. That would be 7th order of the turbo. There's 72nd order of the gear mesh. We select a statistic from the list. We pick a maximum, and the value is to 88, and we can add it to the list. In this case, we got to replace because we're editing. If we were to come down here, we'd get a new one. So now that we've got now that we have our 70-second order on the list, we work backwards a little bit more to see where that came from, and that's this one right here. If I double-click on it, you can actually see the selection on the time frequency diagram that represents the energy of the 70-second order. So the front microphone was selected, the engine tachometer was selected as the reference for order tracking. It's a 4 pulse per rev tachometer. The 70-second order was selected for extraction. We used a 50 order wide bandwidth, or 50 hertz wide bandwidth, I should say, 50 hertz. And we selected the energy underneath that black line right there is reconstructed in red here, and that represents the order. That's the order there in red. So we restrict the range from 850 RPM to 1,800 RPM. Our triggering logic allows us to find 850 RPM 1.93 seconds in. It allows us to find 1,800 RPM 8.26 seconds in. So that is the amount of data that's actually used to compute the order. This would be the instant spectrum following the cursor. So at any point in time, the individual spectra will show up down below there. And then this is the order cut, the red curve. So when we hit the extract button, we record the 70-second order on the feature extraction list. And then when we come over here and we look at that, we just see its envelope or its magnitude. The magnitude of that order is then subjected to an algorithm for max. That gives us a metric. We pop on the decision tab, and we define our decision for 70-second order, and there's our pass-fail. So let's do one from scratch. Let's do just a spectrum. So let's pick a different channel. Let's pick the let's pick this block probe accelerometer. We're going to do an order domain spectrum. So if we begin with a time frequency diagram of the block probe from our channel list, we hit the resample the angle button. This particular tachometer we'd like to select for resampling is the engine tach, and we're going to go out to 128 orders. So we do that, the data file resamples to 128 orders, which represents 256 points per revolution. And then we see that the time frequency diagram now has an order axis against, in this case, if I make that visible, that will be against revolution, so 246 revolutions of the engine crank. The minute I hit the spectrum button, down below here, I get an order domain spectrum. If I extract that order domain spectrum to the feature extraction list, and then go to the feature tab, I can find my order spectrum there. I'm going to do a computation on it. We'll do a simple band power, and we end up with 19.8 dB. If we were interested in restricting that a little further, we might just zoom in on a section of it here. For example, turn on a couple DC button. There it is. So we bring these to center. Say go left and right, maybe the first 10 orders or so. And then the band power represents the result of the energy underneath the curve in between the two cursors. So then we give it a name. We'll call that band power, and we'll extract that. That's now one of the metrics on our metric extraction list. And then we go to the decision tab. I'll double click on this empty line here, give it a metric number, let's call it 004. Select the band power metric right there, value is to 11.5. We're going to pass if it's greater than 11. We're going to associate it with the band power feature, insert it on the list, and now we have a new test. And that's how you design a metric in Shield. Now there are many variations on the theme that we can use following through this process. All we have to do now is save that configuration file, and this one's called SAE Engine Sweep. All computations are now recorded, and we can use that file, put it on our NVH controller, and from then on, every time a measurement is made and that configuration file is selected, we'll see all these computations happen. So that is your brief introduction to Shield. I hope you'll join me for more of these demonstrations as we continue to develop your understanding of how Shield works.